Welcome back, folks. Joe Lamb here, excited to bring you another chapter in our 1030 Introduction to General Organic and Biological Chemistry journey today. We're skipping around just a little bit because this particular chapter applies more to the things that we ended with in our last unit. That is, if you remember, we focused on building Lewis dot structures, determining molecular geometry and polarity, and the real focus is on the last two things that are listed here, phase changes and intermolecular forces. So the fact that molecules are polar, the fact that they have certain geometries determines what type of forces exist in between different molecules. So if you've got a bunch of water molecules next to each other, there are certain forces that attract water molecules to one another. You see this every day. If you were to, say, put little droplets of water and put them on a penny, if you've ever tried to do that experiment before, or if you filled a cup of water up to the brim and notice that you can actually fill it a little bit above the top of the lip of the cup, that is due to the fact that water has attractive forces in between the different molecules, and that is directly as a result of the polarity of the molecule in addition to the molecular geometry that it exhibits. So this is a good time for that unit. We'll also dive into what's called kinetic molecular theory, which describes molecular movement, how that differs between solid, liquid, and gases, how certain things take certain shapes, that some have the ability to expand, some take the shape of their container, some don't. We'll examine those as we continue through the lesson for today. So that being said, there are 4 concepts associated with kinetic molecular theory of matter. That is how we measure molecular movement, how that movement differs based on different states of matter, etc. We should be able to describe the roles that kinetic energy and potential energy play in determining the physical state of a system. So the energy of movement, the potential energy that certain molecules have, how does that impact physical states? Use kinetic molecular theory concepts to explain differing physical characteristics of solid, liquid, gases. Know the terms used to describe various changes in states of matter in and of themselves. Characterize processes as exothermic or endothermic. Are they energy releasing? Do they take in energy? And then distinguish between the 3 types of intermolecular forces and correlate them to key physical properties such as boiling and melting point. So I think things are going to be a little bit shorter than last time. That doesn't mean that they aren't as important. Really no math associated with this, but we do need to be able to analyze the structure of molecules very well. So being able to draw Lewis dot structures, determine their geometry and their molecular polarity is going to be very, very important moving forward. So before we begin that discussion, let's talk a little bit about kinetic molecular theory and understand the concepts of solids, liquids, and gases and how those different states of matter, differ from one another. We can characterize the 3 different states of matter by different properties, the first being volume and shape. We can also characterize them by their density, their compressibility, which is the change in volume with the pressure change. Some particular states of matter have a greater ability to be compressed into a smaller space. And we can also examine some of these properties based off of thermal expansion. That is a change in volume with a change in temperature. So I've put a little chart here just to give you an idea of the different states of matter and how they differ from one another. We're going to analyze each one of these. We'll analyze them individually, but this chart really gives you a good idea of how volume and shape are determined based on the different states of matter, density, the ability for something to be compressed, and then the concept of thermal expansion. That is when you add heat to something, do the molecules expand or do they not expand? So let's dive into a little bit about kinetic molecular theory in and of itself. What is it? How do we describe molecular movement? And the first being that matter is composed of tiny particles, either atoms, molecules, or ions, and that they have definite and characteristic sizes that don't change. So for example, sodium, sulfur is sulfur. Each of these different atoms has a different number of protons that are associated with it, and that results in different physical and chemical characteristics. So it's pretty straightforward here. Just matter is composed of atoms, but different types of matter are composed of different types of atoms in and of themselves. So pretty easy to figure that out. The particles are in constant random motion and possess what is known as kinetic energy. That is the energy of movement. So regardless of what state of matter you are in, whether you are solid, liquid, or gas, you contain some form of kinetic energy. Now, the kinetic energy of different states of matter is going to be different because molecular movement in, say, gases, for example, is much greater than that of molecular movement in, say, solids or liquids. Another thing to keep in mind is potential energy, which is the potential to do work. So if you see the young lady holding the ball up at the very top of the step that's there, the ball has very high potential energy, meaning it has the high ability to do work. Once it's released, though, that potential energy gets transformed into kinetic energy because the ball begins to move. So I think the key thing here to understand is that when we refer to kinetic energy, we're referring to the energy specifically of the movement of the particles that exist within that particular state of matter. Now, particles interact with one another through attractions and repulsions and therefore possess some form of potential energy. Now, that's stored energy based on the position, condition, or composition, just like what we talked about on the right-hand side here. The young lady that's holding the ball here has very high potential energy because it has stored energy based on its position. Its position is very high. Gravity is going to allow for the transformation of that potential energy into kinetic energy. One thing that we've already discussed a little bit is Coulomb's law, and Coulomb's law is the concept that oppositely charged particles are going to attract one another and similarly charged particles are going to repel. The strength of that relative attraction or repulsion is directly correlated to how close those molecules are to each other. So if you think about a positive and a negative, well, they're going to have a lot of electrostatic attraction to one another. Opposite charges attract due to Coulomb's law. Two negative charges and two positive charges are going to have electrostatic repulsion from one another. That is, they are going to want to repel one another. And again, the relative strength of this is directly correlated to how close those molecules are. It goes, again, directly back to Coulomb's law, which we talked about. The relative strength of attraction of oppositely charged particles is correlated to two things. First is the magnitude, or the strength of the charge, and the second is the distance between those individual charges. We're primarily going to focus on the distance between them for this particular point. Number 4 here is that the kinetic energy of particles increases as the temperature increases. When people tell me, what's temperature? Or when I ask that question, what is temperature? A lot of people tell me it is heat. And heat is actually different than temperature. Heat is the transfer of energy from one object to another. Whereas temperature is just simply the measure of the kinetic energy of the particle. So anytime you take the temperature of something, you're actually testing or taking a measurement of how quickly those molecules move around one another. The higher the temperature, the higher the kinetic energy, and therefore the greater the molecular speed. And if you notice on the right-hand side here, a little bit about energy transfer. Energy transfers from hot to cold. So if you take a warm body and you allow it to touch a cool body, the warm body is going to transfer its energy to the cool body until both are what become known as thermal equilibrium. That is, they end up having the same amount of energy and thus the same temperature. It's a little more complex and beyond the scope and sequence of this course, but just to give you a little idea of what's going on here. And then lastly, with kinetic molecular theory, particles in a system transfer energy to each other through elastic collisions. And when I refer to elastic collisions, I simply mean collisions that don't lose energy. So energy is not lost to the environment in those collisions. Energy is always transferred from one body to another. Is that always 100% the case? No. Energy can be lost through many different types of energy transfer from one to another, but we make that assumption in kinetic molecular theory because it does make our lives a little bit easier. Now, if you've ever seen one of these before, this is a great demonstration of how kinetic energy ends up getting converted into potential energy and vice versa. So you notice that the individual, and this is referred to as a Newton's cradle. You probably remember this is like a little clacky ball machine thing that probably sits on, maybe some of your desks or a parent's desk or something like that. But when the ball is being raised, it has very high potential energy and very low kinetic energy. But when the ball is released, the energy is transferred through one ball and then through all of the other ones, so that way the ball that is on the right-hand side here ends up getting a lot of molecular movement. And one of the reasons why this goes back and forth a lot, if you've seen one of these, is due to the fact that the collisions are mostly elastic. Now again, this doesn't go on forever. That ends up violating the law of conservation of energy, where not all energy gets 100% transferred. Some of it does get lost in the environment, and then over time, eventually this thing dies out and you don't get the click, clack, click, clack anymore. Because some energy is lost. If energy were not lost and these collisions were 100% elastic, then this thing would go on forever, but we know that that's not the case. So differences with solids, liquids, and gases really do primarily focus on the relative amounts of kinetic energy and potential energy. And I want you to consider water and its temperature and its state of matter. So let's do Celsius, because that's what we should be looking at here in our class anyways when we look at water. Water freezes at 0 degrees Celsius. So the lower the temperature, the more likely water is to be in its solid state. Below 0 degrees Celsius, it's in its solid state. Anywhere between 0 and 100 degrees Celsius, it is in its liquid state, and anything higher than 100 degrees Celsius, it is boiling, so it would become a gas. So when we think about kinetic energy, we can think that things with low kinetic energy tend to be solids. As you increase the amount of kinetic energy, we get a phase change going from a solid to a liquid, which is known as melting, and we end up with a different state of matter with a higher kinetic energy. And then eventually we continue adding in energy. The molecules will continually move and increase their speed more and more, and eventually they boil, in which they have so much energy that they readily become a gas. So we can really think about the differences between solids, liquids, and gases and the relative amounts of kinetic energy that those things have. Things that are solids are going to have relatively low kinetic energy or low temperatures, and things that are gases are relatively high kinetic energy and have high temperatures. Now, when these things change phases is dependent upon the substance in and of itself. In fact, I'm looking at a glass of water right now. It's probably about 22 degrees Celsius inside my house. The water is a liquid. However, the Xbox controller that's next to it is a solid. So the Xbox controller is made up of different matter than, say, the water is. So its phase change from a solid to a liquid is going to be at a different temperature than, say, that of water. But we can keep a couple things in mind when we look at different states of matter and their properties. And this applies across the board regardless of the substance that you have. Solids are going to have much more potential energy than kinetic energy. In fact, the molecular movement is said to be vibratory. That is, the molecules don't really bounce off back and forth, but rather they just kind of vibrate in place. Solids still have molecular movement, it's just less than that of things like liquids and gases. We could also say that they have much more potential energy because if you remember, potential energy is directly correlated to electrostatic attraction. That is how close the atoms are to each other. Well, in a solid, the atoms are very, very close to each other and as a result end up having a very high potential energy. They have a definite shape and volume, meaning that if I look at my Xbox controller, it has a definite shape. It's not going to change because it is a solid, and its volume does not change as well. It has a high density, meaning that the molecules are very tightly compacted around each other. They're very, very close to one another. They have a very small compressibility. That is, they have a very low ability to be compressed. They're already quite compressed, so being able to compress it even further is very difficult. And solids also have very small thermal expansion. There's just not a lot of room for molecules to separate and move apart from one another. Liquids are a little bit different. The potential energy and kinetic energy are roughly that of the same magnitude, and that is because the kinetic energy is a little bit higher than that of a solid, but the potential energy is a little bit lower, and that's because the molecules are not nearly as close to each other as they are in, say, a solid. It has an indefinite shape but definite volume, so I have a 12-ounce Diet Coke sitting next to me. If I were to pour that into a different shaped glass, it will take the shape of the container, so we can define it as having an indefinite shape because it takes the shape of the container I put it in. However, the volume is definite because there is still 12 ounces of liquid that's present regardless of what container I put it in. We would still refer to it as having high condensity. The compressibility is still small but greater than that of a solid, and it has a small amount of thermal expansion, very similar to that of a solid. Gases are very different because there's a complete dominance of kinetic energy. There's a complete dominance of the movement of the molecules over potential energy. There are very little cohesive forces in a gas because the molecules are spread out very far apart, so they rarely or don't interact with each other very frequently. It has an indefinite shape and volume, so it takes the shape of the container that it's in. And because it has an indefinite volume, that means it has the ability to be compressed. You can think of compressed gas tanks that you've seen in hospitals, or things like propane tanks, which contain compressed gas as well. Gases have very low density, that is, the molecules are spread out very far apart. As we mentioned before, they do have a very large amount of compressibility and have some thermal expansion. As you heat a gas, it gets the volume gets larger. That's essentially how hot air balloons work, is that you heat it and then it expands, becomes less dense than air, and the hot air balloon rises. And then when you cool it down, the molecules get closer together. The air in the balloon becomes the same density as normal air, and then the weight of the balloon in and of itself just allows it to travel down closer to Earth. So keeping all of these things in mind in regards to solids, liquids, and gases is pretty important. I would also make sure that you understand what these look like on a molecular level as well. Solid molecules are going to be compact and very close together. Liquids are going to have the ability to kind of move over the top of one another, which is what allows it to have that indefinite shape. And then gas molecules are going to be very, very far apart where they rarely have the opportunity to interact with one another. So another thing I want to bring up here is our changes in state, and these are things that we've already talked a little bit about previously, but you should be able to tell me what goes on with the individual changes of state that are listed here. So some of these are very straightforward, some of these are a little more difficult to understand because we don't use them in our everyday vocabulary. But things like melting and freezing, melting is going from a solid to a liquid, freezing from a liquid to a solid. Evaporation and condensation, liquid to a gas and gas to a liquid. Sublimation and deposition are much less common and require special circumstances. One good example of sublimation that I'm sure I've talked about previously is dry ice. You can actually buy dry ice at Meijer. It's expensive, but it is frozen carbon dioxide, and at room temperature and at standard pressure, it will go directly from a solid into a gas, completely bypassing the liquid phase. So I would just make sure that you understand all of these different changes in states of matter and how that affects things like kinetic energy, potential energy, how close the molecules are to each other, whether they have indefinite or definite shape or volume, density, thermal conductivity, etc. And one of the things that is unique about some of the substances we're going to be looking at is their ability to interact with one another. So one of the things that we've talked about are different types of bonds, things like ionic bonds and covalent bonds. But bonds in between different molecules of the same substance play a huge role in physical and chemical properties. So if you take a look at the example here of these meniscuses, I never learned the plural of that because I've never had to describe more than one. Go figure. You think you'd have a couple degrees in chemistry and know that, but I don't. Life goes on. But you can pour water in a cup, and obviously you can see here on the right-hand side that the water actually goes over the lip of the cup. And the reason it's able to overcome the force of gravity and not be pulled down to the sides and pulled off of the cup itself is due to the fact that those water molecules are attracted to each other. And the attractions to one another in these water molecules are referred to as intermolecular forces. That is, these are forces that exist between different molecules. And I'll bring up the FYI here because I do mention that this is a big deal, and it is a very, very big deal. Properties of different substances differ tremendously, and the reason why is it's primarily due to the forces that exist between different particles. So intermolecular forces are forces that exist between a molecule and another molecule. So you notice that I have 5 different water molecules that are here on the diagram on the right-hand side. Each of those water molecules is going to have some type of interaction with the other molecules that is going to form some form of attraction between them. And the relative strength of that attraction determines what types of physical properties exist. If you think about phase changes, right, let's say we're going from a liquid to a gas here, and we have some liquid water on the right-hand side. Remember that liquid water molecules are very, very close together. But if I want to convert it into a gas, we have to break those molecules or break the forces between the different molecules and spread them out really, really far apart. Because remember, when we do a phase change, we still have water, right? So what we're going to do here is we're going to break the bonds that are the dotted lines here. We're not going to break the solid line bonds because remember, if we do so, we no longer have water. But by breaking the dotted lines, the water can then go from a liquid to a gas. The molecules are not attracted to each other anymore. They can be really, really far apart. Well, the strength of those attractions, that is the strength of the dotted lines, determines things like boiling point, right? Boiling point is the temperature at which water is converted from, or substance rather, is converted from a liquid to a gas. Well, the higher that boiling point, the more energy is needed to break the bonds that are the dashed lines that are here. And the strength of those dashed lines is based off of Lewis dot structures, molecular geometry, and polarity. So this is where all of this comes back. And all of this is going to be part of our discussion moving forward, is to recognize what types of intermolecular forces exist. It's one of the most important things that we're going to discuss in this class in regards to how structure determines function. So keep that in the back of your mind as we move forward. Now, as I mentioned before, forces exist between different molecules are called intermolecular forces, and I want to make sure we differentiate them completely from covalent and ionic bonding. Covalent and ionic bonding are referred to as intramolecular forces. That is, forces that exist within the same molecule or within each molecule. So notice here the solid lines that are in water. We established that water is a molecular or covalent compound. So the solid lines that are there are actually covalent bonds. Those are intramolecular forces. They're covalent bonds. The dotted lines that exist between the different water molecules that are here are called intermolecular forces. They're dashed lines because they're typically considered weaker than that of the solid lines of the covalent bonds. And you can see here we have something that is called hydrogen bonding, which we'll discuss in just a moment. But hydrogen bonding is very important not only for these water molecules here and establishing their different physical and chemical properties, but also very important if you've taken a biology course, you understand how important hydrogen bonding is for water molecules inside of the body as well. So let's talk about the different types of intermolecular forces that are present. And there are 3 that we're going to discuss as a class. There are more than that. There's actually close to like 6 or 7 different intermolecular forces. But the 3 main ones we're going to focus on are what are referred to as London dispersion forces. We'll also then refer to dipole-dipole forces and hydrogen bonding. So let's talk a little bit about London dispersion forces. And London dispersion forces occur due to the fact that electrons have the ability to move around randomly around an atom. Right? Electrons don't move in orbits. They don't move in set pathways. They move very randomly. And so at any one given time, all of those negatively charged electrons could be on one side of an atom here. So if I look at step one here, we have a symmetrical distribution of electrons. But if I look at the first atom in step number 2, I notice that all of the negatively charged electrons are on the right-hand side of that molecule. What that does is that creates a slight negative charge on the right-hand side. It makes sense. All those negatively charged electrons on the right-hand side there make that part relatively negative, and then the part on the left-hand side is relatively positive. There's just a nucleus that's there. Again, this is all occurring within the same atom. Well, if we get one of these atoms that looks like this and finds itself attracted to another one that looks like this, you end up with what's referred to as a London dispersion force. Remember, all of this goes back to Coulomb's law. All of this goes back to the fact that opposite charges have the ability to attract one another. So you notice in the first atom there, the negatively charged right-hand side of that atom is attracted to the positively charged left-hand side of atom number 2. Again, opposite charges being attracted there, so you see that little bit of a dashed line. Now, these are what are referred to as temporary dipoles, and that's due to the fact that those electrons are constantly in motion, right? So as soon as this happens, those electrons end up actually moving elsewhere, and the London dispersion force is not as strong or is broken or no longer exists. But they're referred to as temporary dipoles, again, because of the random movement of electrons, which means that these are relatively weak. How do I know if something has London dispersion forces? Well, if it's a molecule or an atom, it will have London dispersion forces. So all molecules are going to have London dispersion forces associated with them. The relative strength of those London dispersion forces is directly correlated to things like molar mass or surface area. I'm not too terribly concerned about that. I just want you to know that if something has electrons, it has London dispersion forces. And since all atoms and all molecules have electrons, they all have London dispersion forces. So again, if you take a look at the concept here, and it's not a great concept, but the blue shading refers to the electron density. That is where the electrons are located in this molecule here. And notice that eventually we end up in molecule A with all those electrons on the left side, which is a bit different. You notice that relative negative charge on the left side there and the relative positive charge on the right side. So what you end up having is what's called an instantaneous dipole. That means that one side of the molecule is negative, the other side is positive. And if this happens in a second molecule, you get some attraction there. Notice that the positive side of molecule A is attracted to the negative side of molecule B. That goes back to Coulomb's law again. It's an instantaneous dipole. It's a London dispersion force. It's very weak. It's instantaneous, so as soon as this happens, it goes back and reverts back to being less attracted to it. But again, London dispersion forces still plays an important role in things like states of matter, boiling point, melting point, those types of things. Now, the next type of intermolecular force we're going to discuss is what is known as dipole-dipole interactions. And the difference here is that these are permanent dipoles that exist between two polar molecules. So one of the big factors here is that the molecules have to be polar in order to exhibit dipole-dipole forces. And that's because there is a permanent dipole, right? We've drawn these before where we've drawn dipole arrows that points towards the atom of higher electronegativity, and we gave it a relative negative charge. And the one that is less electronegative, we gave it a relative positive charge. And what you notice is that the dipoles exist due to the differences in electronegativity. It goes back to the, like I said, the arrows and the little positive and negative charges that we've drawn on molecules when we did electronegativity differences. The negative end of one molecule is attracted to the positive of another. So you see here you have HCl. The chlorine on HCl has a relative negative charge, while the hydrogen has a relative positive charge. And that's permanent, right? It has nothing to do with the random distribution of electrons. It has to do with the fact that chlorine is more electronegative than hydrogen. And so as a result, it will have that permanent negative charge associated with it. It's going to be attracted to the hydrogen, which has a relative positive charge that's associated with it. So in order to have dipole-dipole interactions, the molecules must be polar. And dipole-dipole interactions are stronger than that of London dispersion forces, and it makes sense. We referred to London dispersion forces as temporary dipoles. We referred to them as being weak in terms of their intermolecular forces. Well, because these are permanent dipoles, that is, these molecules are polar, those interactions are going to be much stronger because it's not due to the random distribution of electrons. It's not due to the fact that they eventually go away. It's the fact they're permanent. And because they're permanent, the attraction is going to be much stronger. So that dashed line there is going to be stronger. Now, again, these are still molecules, so these will exhibit London dispersion forces, but they will also exhibit dipole-dipole. What that means is that intermolecular forces are additive with one another, meaning that we're not going to have something with dipole-dipole that doesn't have London dispersion. You're either going to have London dispersion or London dispersion and dipole-dipole, at least at this point. And as I mentioned before, dipole-dipole forces are typically stronger than that of London dispersion forces. It goes back to the concept of the permanent dipole versus the temporary dipole. It's not about the random movement of electrons that just so happen to be on one side and then they eventually go away. No, it has to do with the fact that these molecules have permanent dipoles. One side is relatively positive and the other side is relatively negative. So what we're going to do now is we're going to do a little bit of an exercise. We're going to do some drawing. And we're going to draw 3 molecules of HF and draw the dipole-dipole forces between the different molecules. So a couple things we're going to need to do here. First off, we need to draw our Lewis dot structures correctly. That's step number 1. Secondly, we need to identify which atom in the bond has a greater electronegativity, because that's going to be the portion of the bond that has the relative negative charge. Then we need to think about what part of the other HF molecules are going to be attracted to the parts of the HF molecule you've drawn. Remember, opposites attract. So if we give a negative end to one part of the HF, the opposite end is going to get a positive, and think about what attracts one another. Opposite charges attract. So think about those things. We're going to do the same for H2SE here in just a moment. Take a moment, see if you can do that on your own. Look at what we've looked at previously, and we will do it together in just a moment. We'll see you soon. All right, so the very first thing it asks us to do here is to draw out 3 molecules of HF and the dipole-dipole forces between the different molecules. So first thing we need to do is make sure that we have the correct Lewis structure. So we're looking at HF. All right, and if we go out and draw the Lewis structure, and again, I'm not going to go through all the individual steps on how to do that. You can look at a previous lesson if you want to make sure that you know how to do that. But HF will be drawn like this with 6 dots around the fluorine. And as we go through and try to figure out how the dipole-dipole forces are going to look, what we need to make sure that we do is identify which side has the relative positive dipole and which side has the relative negative dipole. So hydrogen here is the relative positive dipole, fluorine relative negative. And I'll do that here in red. Same thing, another molecule of HF here. And again, we draw out the relative positive and negative dipoles that are here. It will give us a really good idea of what parts of each molecule are going to be attracted to each other. And so remember that the positive of one molecule is going to be attracted to the negative of another. So what we're going to do is we're just going to draw a dotted line in between the H of one HF molecule and the F of another. And we do that for both of them here because those are the attractions that are going to exist. All right, so as we go through and draw these, it's important to draw out obviously the correct Lewis dot structure, but also draw out the relative positive and negative charges and then connect them accordingly based on Coulomb's law. Same here for H2SE. We need to draw 3 molecules of that. So HSE. Draw one a little bit different just to give you an idea of a little bit easier way to do this. And again, relative positive and negative charges, that's based off of the electronegativity value. Selenium has a higher electronegativity than that of hydrogen. So this is our relative negative, and these are our relative positive. And we do the same for each part of the H2SE molecule. And so again, opposite charges will attract, so the hydrogen of one is going to be attracted to the selenium of another. Now what you may notice is that when I drew out my third one, I already kind of had in the back of my mind what the orientation is going to look like. Remember that these molecules are going to be relatively close together, so they're going to orient themselves in a way where opposite charges are going to be most attracted to each other. It doesn't make much sense that the hydrogen here is going to be attracted to the selenium all the way over here. In fact, it's most likely going to be repelled by that hydrogen that's down here below, like what you see here. These two things are going to want to repel one another. But notice how I oriented my molecules on the right-hand side here. This H2SE is oriented in a certain way, but this one's oriented in a way where the negative charge is relatively close to the positive charge. So when you go through and finish up your work, this is the kind of stuff I'm looking for. HF here, these are perfectly fine because the molecules kind of naturally orient themselves the correct way. But with something a little more complicated, you really want to make sure that you dive in and understand how you go through and do this. So keep in mind, again, draw your Lewis structures correctly. That's the very first thing you need to do here. When you look at the bond, indicate which part of the bond is going to have that relative partial positive charge and relative partial negative charge. And again, that's based off of the electronegativity. Whichever is closest to fluorine is going to have that relative negative charge. And then find your opposite charges and find a way to attract them to one another. Pretty straightforward, all right? Let's move on. The last type of intermolecular force we are going to discuss is hydrogen bonding, and this is the strongest dipole-dipole interaction, which is another indication that this molecule has to be polar. And specifically, we're looking for a hydrogen of one molecule that is covalently bonded to an oxygen, nitrogen, or fluorine that is attracted to the oxygen, nitrogen, or fluorine of another molecule here. And the reason why this is the strongest has to do with the fact that oxygen, nitrogen, and fluorine are the three highest electronegativity atoms that are on the periodic table, and so the large difference in electronegativity makes those relative positive and negative charges that we identified on dipole-dipole intermolecular forces even stronger due to the bigger difference in electronegativity. But notice here you have an oxygen that is covalently bonded to a hydrogen, and there's an attraction between the oxygen of that water molecule and the hydrogen of another. So you'll find that these look very, very similar to dipole-dipole forces, but specifically you're looking for oxygen, nitrogen, or fluorine in the molecule. It has to be covalently bonded to a hydrogen to result in such a large difference in electronegativity, and it has to be attracted to a hydrogen that's attached to another molecule. So again, it's fairly straightforward to identify and fairly straightforward to draw out. Just keep in mind that when you're looking for polar molecules, you're looking for things that can make hydrogen bonds. You're looking for things that are polar, first off, that have the ability to form dipole-dipole forces. And then you have to look and see, do I have a hydrogen that's covalently bonded to an oxygen, nitrogen, or fluorine within the molecule? If that's the case, then yes, you're more than likely going to find hydrogen bonding that exists in between the different water molecules or different molecules thereof of that particular substance. So again, what I'd like you to do, very similar to what we did last time, we're going to draw 3 molecules here of H2O and show the hydrogen bonding that's between them. I'll be with you in just a moment. So here we're going to follow the exact same steps that we've done previously. So how we identify and draw out hydrogen bonding is very similar to how we do dipole-dipole intermolecular forces. We draw out 3 molecules of H2O and show the hydrogen bonding between them. So let's draw some H2O. And again, we want to try to figure out what types of We want to figure out which sides have the relative positive and negative charges for each of these. Oxygen has a greater electronegativity, so it will have the relative negative charge, while hydrogens have the relative positive charge. And again, I didn't orient these very well, but you do get the idea that the oxygen of one is going to be attracted to the hydrogen of another. Opposite charges attract. Hydrogen, oxygen of one, hydrogen of another, oxygen of one, hydrogen of another. If you wanted to orient this a little bit better, I would suggest maybe you draw out your water molecules something like this. Because again, you can see here that these, the hydrogen and the oxygen, are much closer to each other. And so that gives you a better indication of where the hydrogen bond forms. And again, that relative strength of hydrogen bonding as well. Those molecules are closer together. The hydrogen and oxygen are near each other. You're going to show that that bond is a little bit better. These don't really do a great job of that. I mean, it shows that you understand the attraction, but orienting the water molecules in an appropriate way, or orienting any of the molecules in an appropriate way to get those negative and positive charges closer to each other represents a better visual representation of the actual interaction of the molecules themselves. So keep that in the back of your mind as you think about these types of interactions. All right, let's move on. So another important indication of the relative strength of intermolecular forces, as we look at the diagram on the left-hand side here, it refers to the intramolecular force. That is the covalent bond that exists between the hydrogen and chlorine. That is going to be a relatively strong force when compared to that of the intermolecular force, which is weak. So what that tells us is that when phase changes happen, we're going to be breaking the weaker forces prior to breaking the stronger forces. So the intermolecular forces will break first, resulting in a phase change. Remember, with phase changes, we do not change the chemical formula of the compound. So whether we're going from a solid to liquid, liquid to gas, if we're undergoing a phase change, it still should remain the same compound, which tells us that we're breaking the forces in between the different molecules rather than the forces within the same one. And again, here is just a brief way of summarizing the interactions that you see based off of intermolecular forces. So you see London forces on the right-hand side here. You see dipole-dipole interactions and hydrogen bonding. So all three of these are very important. It's also very important to make sure that you're able to identify these types of forces that exist within those molecules. So if I give you a molecule, you should be able to identify what types of intermolecular forces it has. Remember, all things have London dispersion forces. Dipole-dipole forces exist in between polar molecules, and hydrogen bonding occurs when the molecule is polar and you have a hydrogen that's covalently bonded to an oxygen, nitrogen, or fluorine. So a variety of ways to make sure that you can show the intermolecular forces and describe them. And then the big thing here is what's coming up next, which is the relative strength of those forces and how that impacts physical properties. So notice the relative strengths that are here. Dispersion forces, the strengths tend to be relatively weak when you look at the amount of kilojoules per mole. It's just a way to quantify energy. Dipole forces occur in polar molecules, and they're quite strong as well. Hydrogen bonding is a specific type of dipole force, and you notice that the relative strength is even higher than that. So this is just, again, a brief summary of the three major intermolecular forces. Now, there are many others that are out there, but these are the three major ones that we're going to go through and discuss. So what I want to do here is take some time and identify which has the stronger intermolecular forces. Take some time, look at these individual molecules here. Think about the different types of intermolecular forces that are present within them. So the first thing you need to do is draw out the Lewis structures, determine the molecular geometry, the polarity, and then based off of the information we just discussed, determine what types of intermolecular forces are present. Remember, the more intermolecular forces it has, the stronger it's going to be in terms of intermolecular forces. So something that has London dispersion is going to be relatively weaker than something that has London dispersion and dipole-dipole, which would be relatively weaker than something that has London dispersion, dipole-dipole, and hydrogen bonding. Obviously, there are exceptions to that, but again, beyond the scope and sequence of this course. Take a few moments and we'll go through it together. All right, so as we mentioned before, the goal here is to determine which has the stronger intermolecular forces. In order to do that, we need to make sure we draw out the Lewis structures for all of these. So first one here is CCl4 and H2O. So I'm not going to go through the individual steps like I would have talked about previously. If you need help with that, check out the last video we went through. I believe that is chapter 5 in order to go through and do that. But that being said, let's draw these out. I may need a little bit more room later on, so we may need to erase some of these, which is okay. And we're going to have that against H2O. Okay, so our next step, once we've gone through and drawn out the correct Lewis dot structures, is to figure out the geometries and the polarities for these. So CCl4 is going to be tetrahedral. Water is bent. This is a non-polar molecule, while H2O is a polar molecule. So, before I do anything else with that information, let's figure out what types of intermolecular forces we have. So, just non-polar, remember that everything has London dispersion forces. But because this molecule here, H2O, is polar, it also has dipole-dipole forces, and there is a hydrogen that's covalently bonded to an oxygen, nitrogen, or fluorine, so this has hydrogen bonding. So the one that has the stronger intermolecular forces is the one that has more intermolecular forces. So in this instance, we can say that H2O is going to be the winner here. It has stronger intermolecular forces than CCl4. All right, let's move on and do the next one. Fancy erasing here. Oh, those little individual dots have got to go away. So we're going to do HBr and CO2. So HBr's Lewis structure is going to look like this. And CO2. And again, the more of these you do, the better, especially if you're going into chemistry long term, because these are kind of committed to my memory, but regardless. Both of these are going to be linear. Okay, so this molecule here is polar and CO2 is nonpolar. Again, you could draw your dipole arrows if you want to help you with that. Dipole arrows and CO2 are going to cancel. HBr, they are not. So again, we look at the relative intermolecular forces that are present here. Both these will have London dispersion forces. But this molecule here is polar, so it will also have dipole-dipole. Now, this molecule, this HBr, will not have hydrogen bonding. There's no hydrogen that's covalently bonded to an oxygen, nitrogen, or fluorine. So even though that is the case, HBr still has stronger intermolecular forces because it has both London dispersion forces and dipole-dipole, while CO2 just has London dispersion. So HBr is going to be the one with the stronger intermolecular forces there. All right, let's get these erased. Move on to the next one, pH3 versus NH3. So let's draw these out. And NH3 over here. All right, they are both trigonal, pyramidal. They are both polar. Again, that single lone pair on that central atom is an indication of polarity, at least for my class. I know different professors do things a little bit differently, which is fine. We go through these. Both are polar, so both will exhibit London dispersion forces and dipole-dipole. But NH3 has a hydrogen that is covalently bonded to an oxygen, nitrogen, or fluorine. So the difference here is that NH3 is going to be able to have hydrogen bonding. So when I compare them, NH3 is going to have stronger intermolecular forces than pH3 because it has all three, whereas pH3 only has two of the three. So that's how we determine that one. I'm going to go ahead and skip ahead to the last one here. I know I'm skipping one. That's okay. I'm allowed to do that. I am the teacher. H2O and H2S. Both are bent. Both are polar, which means that both exhibit London dispersion forces and dipole-dipole. But again, the difference here is that H2O has an oxygen that's covalently, a hydrogen that's covalently bonded to an oxygen, nitrogen, or fluorine. So this has the ability to hydrogen bond. So as a result, H2O has the stronger intermolecular forces. Now, the one that's in the middle there, that CH4 versus SiCl, I include this sometimes. It just depends on the group of students that I have. But what you're going to find is that both of these are actually non-polar molecules. Sorry, there's a rogue electron like here. I'm trying to get, there we go. Sometimes it's hard to get rid of like individual electrons and whatnot. Both these are actually tetrahedral. And both of these are non-polar. So what you'd find is that both actually have London dispersion forces. Well, how do we compare two molecules that only have London dispersion forces? The one that has the stronger intermolecular forces most of the time is going to be the one that has the higher molar mass. Remember, that's based off of the information on the periodic table. So CH4's molar mass is somewhere around 16. SiCl4's is much larger than that. Just doing it off the top of my head, it's like 71, which is 142, and 29. It's like 171 grams per mole, something like that. So in this case, SiCl4 has the stronger intermolecular forces. The only time you're going to compare molar mass is if they both have the same types of intermolecular forces. And the reason being is that larger molecules with greater molar masses, tend to have more electrons and therefore have what is called a larger polarizable electron cloud. It just means that more electrons have the ability to shift to one side or another to create those instantaneous temporary dipoles that describe London dispersion forces. Some people will not cover that. Sometimes I won't even cover that. It depends on the group that I have. But you get the idea here. You're just simply comparing the types of intermolecular forces they have, and then based on that information, drawing a conclusion as to which has the stronger intermolecular forces. All right, so practice with that, and we've got, I think, one or two more things left to talk about, and we will be done. So what we do with this information in terms of the relative strength of intermolecular forces is we correlate that to the boiling or melting point of a sample. And the more intermolecular forces that are present means it requires more energy to overcome the forces between the molecules, thus resulting in a higher or melting. So what we do with this information is we can correlate the strength of the intermolecular forces directly with the melting or boiling point of a sample. And simply put, the more intermolecular forces that are present means it requires more energy to overcome the forces in between the molecules to boil them or melt them, and thus resulting in a higher boiling or melting point. So for example, if I compare methane and water, methane is a nonpolar molecule that only has London dispersion forces, and look at its boiling point is negative 162 degrees Celsius. So it is a gas at room temperature. Look at the boiling point of water, though. Water has the ability to hydrogen bond and has a boiling point of 100 degrees Celsius. So notice how the strength of intermolecular forces plays a role in the amount of energy needed in order to boil the substance. The higher the temperature, the more energy is needed to convert that substance from a liquid to a gas. And same with melting it from a solid to a liquid. You notice that the stronger intermolecular forces correlate to a higher melting point as well. So all we're going to do here is we're just going to simply compare the two substances, figure out what types of intermolecular forces are present, and then utilize that information to draw some conclusions. So how do we go through and do this? Well, we draw the Lewis dot structure, we determine the geometry, we determine the polarity, and we identify the intermolecular forces. And then determine the stronger IM forces and correlate that with the boiling point. Now, it all sounds like there's a lot to this, and there is, because this lends itself to what is called claim evidence reasoning. And this is one of the most important concepts I want you to be able to understand as we work through some of this material is the ability to critically think. It's the ability to take scientific information and draw conclusions based on that information. So when you're writing open-ended responses to intermolecular force style questions, I want you to use claim evidence reasoning to discuss that. It is absolutely vital because this is how scientists reason and utilize information to draw conclusions. The first part is the claim. So based on the information at hand, which has the higher boiling point would be an example that we looked at previously. So I would say that water has a higher boiling point than methane. Remember, you are comparing and contrasting. You need to describe both substances as you go through and use claim evidence reasoning. The evidence described the relative intermolecular forces for each molecule and how you drew those conclusions. So I would say that CH4 is a molecule that is tetrahedral and it is a nonpolar molecule and only exhibits London dispersion forces, while water is a bent molecule that is polar and exhibits London dispersion forces, dipole-dipole forces, and hydrogen bonding. So notice I'm providing the complete evidence. I'm utilizing the Lewis structures and the geometries and the polarities to describe what types of intermolecular forces are present within those molecules. And then the last bit here is the reasoning. Compare the two and describe that stronger forces between molecules result in a higher boiling point. So I would say something like, as a result of water having London dispersion, dipole-dipole, and hydrogen bonding when compared to that of methane, which only has London dispersion forces, water requires more energy to break the bonds in between the different molecules as a result of the higher intermolecular forces, and as such has a higher melting point, boiling point, etc. than that of methane. So notice again, I'm using my claim, I'm providing complete evidence based off of everything that we've done the last 2 units, and then I'm using reasoning to describe, okay, this is what I have. As a result of this information, this requires more energy to break the bonds in between the different molecules and thus resulting in a higher melting point or higher boiling point. It is very formulaic, it is very step-by-step, but it is absolutely critical that you can do this. Critical thinking is something that's very important, not just in chemistry, not just in science, but in those allied science fields, those nursing fields, to be able to take information and figure out what I can do with that information and use evidence to be able to reason an appropriate decision is something that is absolutely critical for your success in the allied health field. So, explain which would have a higher melting point, HF or F2, and justify your answer. So what I'd like you to do is to try this on your own. Try a little bit of claim evidence reasoning. First, go through and figure out what is the Lewis structure, geometry, polarity, intermolecular forces. Then utilize that information to decipher which of those you think is going to have the higher melting point, and why. Take a few moments, we'll come back and talk about this in just a moment as I have already prepared a written response. All right, so looking at this information, this is exactly what I would write out. I would write out that HF has a higher melting point than that of F2. Both molecules are linear, however, HF is a polar molecule while F2 is a nonpolar molecule. This indicates that HF will exhibit London dispersion and dipole-dipole forces, while F2 only exhibits London dispersion forces. HF also has the ability to hydrogen bond. HF has stronger intermolecular forces than that of F2. Stronger IM forces require more energy to convert the substance from a solid to a liquid, thus HF has a higher melting point than that of F2. So notice I provided my claim, HF has a higher melting point than F2. I then provide my evidence. My evidence is based off of the geometry, polarity, and intermolecular forces that are present. And then I wrap it up with my reasoning, which is that stronger IM forces require more energy to convert the substance from a solid to a liquid, thus HF has a higher melting point. So I utilize, again, that claim evidence reasoning to decipher how to go through and answer this question. It's so important that you have the ability to do that. One more example of a practice problem I want you to go through and complete. I want you to try this one on your own. Explain which would have the higher melting point, CH4 or SO2, and then again, justify your response. Pause the video, take a few moments, and then we will come back and wrap this up. Thank you. All right, so I'm going to provide the exact same style of explanation I did before. SO2 would have a higher melting point than that of CH4. SO2 is a bent molecule that is polar, while CH4 is a nonpolar molecule. This implies that SO2 will exhibit London dispersion and dipole-dipole intermolecular forces, while CH4 will only exhibit London dispersion forces. The stronger ion forces in SO2 will require more energy to convert the substance from a solid to a liquid when compared to that of CH4. Thus, SO2 has a higher melting point than CH4. So, again, same thing, provided my claim. SO2 has a higher melting point than CH4. My evidence is solely based on the geometry, polarity, and intermolecular forces, and then I wrap things up with my reasoning that stronger ion forces require more energy to convert the substance from a solid to a liquid. So SO2 has a higher melting point than CH4. So what do we do with some other information here? Well, some other interesting points of note that you need to keep in mind is ionic substances. So anytime we do something that's very similar to this, but we're comparing ionic substances will always have a higher melting or boiling point than any covalent substance because ionic melting breaks the intramolecular forces. Remember, covalent substances, when we melt them, break weak intermolecular forces. So notice the melting points of those ionic compounds. They're in the thousands of degrees. CuO, 1,300 degrees Celsius. Al2O3, 2,000 degrees Celsius. It's almost always going to require more energy to melt ionic substances. Remember, ionic substances are in that crystal lattice structure that maximizes attractions and minimizes repulsions. So as a result, it's going to require a lot more energy to break those bonds, those intramolecular forces in the ionic substances, than it would to break the intermolecular forces that exist between different molecules. Remember, those are much, much weaker bonds, much easier to break, therefore a much lower melting point. So I'll give you a moment with this. I'm not going to write it out for you, but I will explain the answer. But in a similar way, I'd like you to go through and justify which has the higher melting point, H2O or KCl. So take a moment and justify your response, and we'll be back in just a moment. So as mentioned previously, when we were comparing covalent substances and ionic substances are always going to have a higher melting point. So how I would justify this, I'd first start my claim, is that KCl has a higher melting point than that of H2O. And my justification is that when we melt KCl, we're breaking intramolecular forces, strong ionic bonds that require a lot of energy to overcome in order to melt the substance. With water, we're breaking weaker intermolecular forces between different water molecules in order to melt the substance. And so as a result, KCl is going to have a higher melting point than that of H2O due to the fact that KCl, when it melts, breaks intramolecular forces, whereas H2O breaks intermolecular forces, which are weaker. So again, provide my claim, provide my evidence, and then justify my explanation. You can never include too much detail with these, but you can always include too little. So make sure that you justify things completely and provide as much detail of an explanation as you possibly can. That's going to get you the most points. And in this particular course, I can tell you right now that 40 points of your final exam is this style of question. So 20% of your grade on your final exam is doing this with the information that's given. So again, take your time, read each question carefully, and practice, practice, practice. Now, when we analyze larger molecules, this isn't that difficult to do, but what we need to do is identify points where we might find dipole-dipole forces and hydrogen bonding, and we do need to keep this in mind and utilize this as justification for higher boiling points. So I'm going to use a couple of these as an example to show you how we can justify larger molecules and their boiling points based off of what we've just gone through and done. So let's go through and analyze these molecules and explain why X has a higher boiling point than Q. So I'm not asking you to tell me which has the higher boiling point at this time. Sometimes I might, sometimes I won't, just depends. But clearly X has a much higher boiling point than that of Q. Well, let's go through and analyze these. Q only contains carbon-carbon bonds and carbon-hydrogen bonds. These are all non-polar molecules. So this molecule is only going to have London dispersion forces that are associated with it. I want you to notice the molecule over here, and I want you to see, is there any way, if we were to go through and draw dipole arrows, to determine the polarity of this substance? And what you notice, there's a couple of ways to notice this. First off, I have a dipole arrow that would go here, that would point between the carbon and oxygen. Remember, we're not going to do any dipole arrows between carbon and carbon or carbon and hydrogen because they're technically non-polar bonds. But between the carbon and oxygen here, I have a dipole arrow that would not cancel. In addition, the geometry around this oxygen is bent, right? And any part of a molecule that's bent, we discussed in our previous chapter, is going to be indicative of a polar molecule. So we can look at this molecule and say, yeah, this is a polar molecule, so it's going to exhibit London dispersion forces and dipole-dipole. Now, is there any part on this molecule where you think you might be able to find hydrogen bonding? And the answer is yes. If I take a look here, this part of the molecule, there's a hydrogen that's covalently bonded to an oxygen, nitrogen, or fluorine. And if that exists within a covalent molecule, you also have hydrogen bonding that's present. So again, analyzing these molecules is not that different than how we analyze the smaller molecules. We just have a little bit more work to do in terms of looking at the molecule and figuring out if it's polar or nonpolar. In addition to that, we also just have to look for places where hydrogen bonding may or may not occur. So it does take a little bit more time to go through and analyze some of these. But again, let's go through and figure out, and let's just compare a couple of these and see if we can figure out which are polar, which are nonpolar, which can hydrogen bond, which can't hydrogen bond, etc. So if I look at pentane and propane, they just contain carbon and hydrogen, right? So these are only going to exhibit London dispersion forces. Methanol is a polar molecule, and methanoic or formic acid is a polar molecule. Again, you have some areas here where those dipole arrows will not cancel. Remember, this part of the molecule here is bent. Same here, it doesn't show it, but it is bent. You also have dipole arrow here that does not cancel. So all three of these molecules are polar. Now, methanol has that OH bond, and methanoic or formic acid also has that OH bond. So these can actually do all three. Here, this one doesn't have that, so this can only do London dispersion forces and dipole-dipole. Now, if I were to ask you to compare the melting points, the boiling points of these substances, you should be able to go through and do that, again, based off of the relative intermolecular forces that are present in these substances. And again, it's all about that claim, evidence, reasoning. Last couple ones here, and I'd like us to go through and figure out which of these is going to have the higher melting point. Okay, or which of these is going to have the higher boiling point, etc. So take a look at some of these. Let's analyze the data that we've got here. You got lots of carbon and hydrogen in this. Okay, it didn't include any lone pairs or anything like that. You do have a pair here of dipoles that will cancel out. The rest is carbon and hydrogen here. So you could venture to go through and say that this is a non-polar molecule. Okay. In some instances, you might say that it's polar, but it will become irrelevant when we look at this molecule over here. You see lots of places where the molecule's bent. Yes, I don't know, I didn't put the lone pair here, but every OH you see here is a place where you see a part that is bent. So this molecule is a polar molecule, and look at all the places where hydrogen bonding can occur. OH, 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 OH. So this can do all of it. London dispersion, dipole-dipole, and hydrogen bonding. Whereas this molecule on this side can only do London dispersion forces. So clearly, this is going to have the higher melting point, higher boiling point. Okay? So again, as we wrap things up for today, what I really want you to recognize is that everything kind of builds on itself. To draw the Lewis dot structures correctly is absolutely critical for determining the geometry, the polarity, and the intermolecular forces that you see in between the different molecules, and those directly correlate to melting and boiling point. So utilize this information, take your time, and again, practice, practice, practice. Use the practice problem sets that are located in Canvas. Go through some of the homework problems that I've gone through and assigned. Watch the video and ask questions if you need to do so, and hopefully that helped you through unit number 7. If it did help you, make sure you leave a like on the video. Feel free to subscribe for more chemistry-related, science, nerdy content, if you will. A few more videos left in this series and I will be done. But thank you so much for watching. Take care, everybody, and we will see you soon in the next video. Peace.